having me. Like Ruth, I'm also a mathematician, but a slightly different mathematician. I'm an applied mathematician at the University of St Andrews. Now, in other universities, I could be a physicist or an astronomer. So I'm kind of in between all those subjects. Now, I'm going to start this talk with a video, and I don't know if the sound is working, so we'll try it. And otherwise, I'm going to pretend to be the narrator and just do the story. So let's see. There's no sound. We'll try it one more time, okay?
For space roughly aligned with the sun's...
Wait, we'll start again.
Ever since we've been pointing spacecraft at the sun, 2 regions on our star have been missing from satellite images. The sun's 2 poles have never been mapped because all the solar images we've built have remained in the ecliptic plane, the swath of space roughly aligned with the sun's equator, where all the planets orbit. A new mission from the European Space Agency and NASA called Solar Orbiter aims to escape this plane and take the very first images of the poles.
The planets are all moving and circling the sun, and so we already have some velocity going one way. If we want to launch up out of the ecliptic, it requires more energy.
To get outside the ecliptic plane, Solar Orbiter uses Earth's and Venus's gravity to slingshot itself into a view of the poles. The only other satellite to fly over the poles was Ulysses, which launched in 1990 to study the solar atmosphere. But Solar Orbiter will be the first mission to capture actual images of this hard-to-reach region. Scientists think the poles could be the missing piece to understanding what drives the sun's activity. Every 11 years, the sun's magnetic field flips. North becomes south and vice versa. This mysterious process has direct effects on Earth. Before the poles flip, solar activity reaches its peak. The number of eruptions increases, sending powerful bursts of solar material that can potentially harm our astronauts and satellites.
Okay, so what I'm going to do in the next few minutes, hopefully, is essentially talk through this video with some of our models and data and help you understand what they were talking about. But just to say, I have a whole bunch of very excited colleagues out in Florida for the moment. Solar Orbiter is due to launch on Sunday, although there's a rumor it might be postponed till Tuesday. So it's currently sitting in its nice little capsule on top of the launching rocket, waiting to be launched, with a bunch of very excited solar physicists hanging around in Florida. Clearly, I got to come to Stirling, but it's nice too. So, I hope everybody knows that the sun is a star. It's a fairly ordinary, boring star if you're an astronomer. And obviously, there's all the planets orbiting around it. Now, this is a picture. It's a kind of a cutaway of what's on the inside of the sun. In the middle is the core of the sun, where all the nuclear reactions happen. That's where all the energy is built up. And then as you move out, it gets colder, and the surface of the sun is about 6,000 degrees. Just underneath the surface, you see where these kind of circles are drawn. This is just a cartoon. It's what we call the convection zone, and I'm going to come back to that on the next slide. So from about 15 million degrees in the center, where the nuclear reactions happen, the temperature goes down to about 6,000 degrees on the surface of the sun. But then, strangely enough, as you move even further out, the temperature starts to get hotter again, okay? And the temperature can reach but it's about 1 million degrees on average, but during a solar flare, it can go up to 10 and even 20 million degrees. And this is a bit of a mystery, okay? You go away from the nuclear core and it gets colder, that's what you would expect, but then all at once it starts getting hotter again. And that's what we call the coronal heating problem, and it's something we still don't understand. Now, the surface of the sun, you might have heard of sunspots. They're kind of dark areas of the surface of the sun, and we call them sunspots. But hopefully you can see in the bottom corner, it might be hidden a little bit, but that's a kind of a zoomed-in image of a sunspot. And right in the bottom right-hand corner is a picture of the Earth drawn to scale. So they're fairly big spots, okay? They're spots the size of the Earth. Now, these spots are regions where there is very, very strong magnetic field, because the sun has a magnetic field that breaks through its surface. Now remember those circles that were drawn just underneath the solar surface a few slides ago? That's called convection, and it's something you know, and if you've ever watched something boil, kind of soup or water or something like that, you have these big bubbles, okay? And that's what happens just below the surface of the sun as well. So in the top left is just a cartoon, but in the bottom right is a movie taken with a new telescope. And it's a telescope out in Hawaii, which has just started. Oh no, don't do that to me. I've moved. See if it comes back. Okay. Sorry? See if we can get it back. Right, it knows it's there. Yeah, it's coming. I'll just hold it here. It's the whole cable, basically. Oh, it's really wobbly. There you go. There you go. All right, it's back. Okay, so I just want you to watch this video because hopefully you can see that that material is constantly moving. And where it's bright, hot gas is bubbling up, and then it cools down and it sinks again, and that's kind of the dark lanes you see around the bright bits. Now, if you think about this magnetic field, it breaks through the surface of the sun and it makes these huge magnetic loops, as you can see in this cartoon, but the feet of the magnetic field is still stuck below the surface where this convection is happening. So what's happening is you get these bright, can't really see it all that well, but you get these huge loops of magnetic field and plasma or fluid stuck to them, and they're constantly being just jostled around. Just imagine you're in a big crowd and everybody's kind of pushing you around. That's what's happening to these feet of this magnetic field. Now what happens if you push and shovel things around for long enough? It's a way of storing energy in the magnetic field, and eventually there's too much energy. And it goes goes unstable, and it releases all the energy, and I'm hoping, if this video plays, you can see these huge bursts of material leaving the sun, and that's called a solar flare. Okay? So if you imagine, you can do it. I'm not going to do it with these cables, because clearly we're not allowed to touch them, because I know all this horribly wrong. But if you imagine just a cable or a garden hose does it as well, if you kind of twist it on one side, I'm sure you've done that at some point, eventually there's a big kink in it. That's an instability, and that's almost what a solar flare is. Now, solar flares are they're not rare, they happen all the time. This is a movie where you stand a little bit further back so you can see the space around the sun, and the movie is over about a week. It's obviously hugely speeded up, but you can see these flares going off in all directions all the times. And we also call them coronal mass ejections, or CMEs for short. Okay? So all this solar material is essentially hurled out into space, and obviously some of that is going to come our way as well. And hopefully at the end of the video you see one essentially hitting the observing spacecraft. So there you go, you can see all this kind of, looks like snow, but essentially what it is all these energetic particles hitting the spacecraft. I hope there's a fairly dramatic one at the end. There you go. Okay. So, what does this do to us? Why should we care? Well, these kind of big mass ejections of solar material travel into interplanetary space, and they've come past the Earth. Now, we have our own magnetic field which protects us from the most energetic particles, and most of it just kind of streams past us. And there's a little video here which hopefully shows that. No sound this time, so that's good. Okay, so you have these coronal mass ejections, they leave the sun, they travel through space, and then they hit the Earth's magnetic field, and you'll see that most of it just streams around us as if we're some kind of like a pebble in this solar storm. But some of these energetic particles do travel along the Earth's magnetic field and hit our atmosphere, and that's the northern lights. Okay? Usually that's just near the poles, but sometimes when you get a really strong solar storm, that comes a little bit lower, and you can see in the bottom, hopefully there, you might not recognize it, but that's actually a picture of St. Andrews with the northern lights from about 10 years ago. So that's just pretty. But all these energetic particles do actually do some real damage. When they hit satellites, they can cause damage to the solar panels of the satellites. They can short-circuit the electronics, which just makes the instruments stop working. But they can also do serious damage and health problems for astronauts, because astronauts are no longer in this kind of protected magnetic bubble around the Earth. It's a bit dramatic there. It's like nausea, vomiting, cancer, death. It's maybe not all that bad. Now, if you're going for a trip to the moon, it's apparently 10 days there and back for a trip to the moon, and you've got a good chance of avoiding one of these big solar storms. But if we're really serious about traveling to Mars, it takes about half a year to get there. You can't avoid these solar storms, so we need to think of a way of protecting the spacecraft. And then when you get to Mars, Mars doesn't actually have a strong magnetic field. So there's no nice magnetic bubble around Mars to deflect all this energetic material coming from the sun. So not only do you have to survive getting to Mars, you then have to come up with a way of living on Mars, or at least staying on Mars for a little while, protecting yourselves from these solar storms. And that's all I had to say. The last slide I have is just some pictures of the sun. You can maybe come and look at my laptop later if you want, because I do look a bit better on my screen. But I downloaded these pictures just before 9 o'clock this morning, and this just shows the atmosphere of the sun in lots of different temperatures. That's all. Thank you very much
indeed, Ineke.
Hold on, yeah, well, I'll try and hold on to it.